Hey there, everyone. My name is Ryan Schul. Welcome to my analytics channel. So today I want to talk about rideshare demand forecasting and dispatch optimization. We will look at some examples using Uber data, and I'm going to create this data synthetically because I don't have access to their actual data. Only they have that, right? But I want to try to understand how their algorithms work, and presumably they do try to optimize this. I Googled it and I got this as a result. Yes, Uber extensively uses sophisticated optimization algos to manage and operate its rideshare business. Okay, so that's kind of what you would expect from a company of that caliber, right? So the keys to optimization are matching and allocation, route optimization, dynamic pricing, also known as surge pricing, demand prediction, system efficiency, obviously, right? That's the whole goal of optimization, to try to do things as simplistic as possible, and not really as simplistic, I'm sorry, as efficient as possible, right? You want to make it as simple as it can be, but not oversimplify the problem, okay? But it is interesting to know that, um, like it says here, once the rider is matched with the driver, the app's navigation provides the most efficient route. So that makes sense. But the algorithm isn't just going to match the nearest driver to the nearest rider if there's going to be a few riders that share the same car, because you can share a car with another person or a couple of people, right? So it's trying to optimize how it matches the closest car to the closest driver, right? To reduce the driver drive time and rider wait time. But also, if it has to pick up a couple more people, you have to incorporate that into the mix and accommodate every request, right? So let's take an example. Um, let's take a look and see from this example that I created how they probably do this. Now, again, I don't work for Uber. I certainly don't have their data. I'm not, um, sharing anything that's confidential or classified information here. I'm creating it synthetically, but I think it is going to be pretty representative of the type and the style of data that they deal with, or pretty close. Again, if you don't have the exact data, and if you can't broadcast it on YouTube because it's classified information, obviously you can't do that. But we can create a synthetic data set to kind of simulate how this might work. Okay, so I said this in many other videos. If you have no data, you have no analysis, you can't do the project. If you have no data, you can create your own data using a variety of different techniques. You want to make it as accurate as possible, because when you feed it into the machine learning algorithms, it's going to make forecasts and predictions into the future, right? And if you are feeding garbage into the model, it's going to get confused really quick and it's not going to know what to do. But if you send in refined, cleaned, um, very structured data, then the model can figure out very quickly what's coming in and what the output needs to be. Okay, so let me show you how to do that. We have a few parameters that we create at the beginning over here. So minimum frequencies, random seed, all of these problems start with a random seed. Pretty much all these predictive analytics always use a random seed just to get going. It's almost like even in the lottery, when the lottery system is picking winning tickets, it's going to be random. They need the random seed process or some type of randomizer to go ahead and like kick off the whole process of which lottery balls to pick, right? So, or which lottery numbers are going to come up. So this is certainly not about the lottery, right? But the concept is kind of the same. Where do you begin, right? When you start your journey, where do you begin? Most of the times it's actually in a random point, okay? So we want to look at things like the days. I'm going to pick a start date here of January 6, 2025. I want to look at the dates and the frequency of those dates. We are going to assign timestamps, okay? And then we're going to look at a couple different zones, right? So these cars are probably going to drive in different zones for the most part. I don't think the Uber driver is going to go from New York to Nebraska. That would be highly unlikely, although I think I did hear a couple of weird stories where somebody took an Uber like halfway across the country and then jumped out and they never paid for it, right? But that is certainly an outlier example. That's the exception, not the rule. So typically these cars will drive in different zones. Okay, and we need XY coordinates to understand what those zones will look like. So I'm actually going to create a sine daily and a cosine daily. The sine is going to give us the y coordinate. The cosine is going to give us the x coordinate, so we can see where these cars are on a map or some type of visual plotting representation of a map, right? We want to know where the cars have been, where they're going next, and try to understand how we're going to plan these routes to make it efficient and optimized. Okay, and there are a couple more things that we need to collect here. DOW is day of the week, hour of the day, and then bucket in hour, because certain hours can be in high demand. Rush hour, right? Probably, I'm just guessing, like New York City, maybe 8 to 9:30 a.m. And then in the evening, probably 4 to 6 p.m. when a lot of commuters are going to work and coming home from work. Those are probably going to be peak hours, maybe Friday night, 8 to 10 p.m., going out with friends to different bars and restaurants or whatever, right? So that would be a perfect example of high utilization, in demand. Google, sorry, I have to take this call. I'll be right back, guys. Sorry. Okay, so that was my son calling me on the phone. When he calls, I can't say no. It's just 9 years old. But he can say no to me all the time, right? You know, his favorite word is no. So yeah, so we have the y coordinate, that's the sine daily, and the x coordinate. So we need the x's and y's so we can see where these Uber cars are driving to, right? It's like latitude and longitude coordinates, right? And also, this helps us to accommodate a changing from midnight into the next day. So from 0 to 23 is easy for the computer, but when you get up to midnight, like 23:45 and 00 colon 00 are 15 minutes apart, but numerically they're 23 and they're 0, right? So they're very different. So you have to just make sure the computer interprets time as time, and if it's not time, it's not time, right? But you can't confuse time for non-time because you're going to have all kinds of nonsense results, right? So we accommodate that right there. We are using our zones over here. So like I was talking about, like these Uber drivers are going to go pretty much in one zone or maybe cross over the border into another zone. They're not just going to go helter-skelter all over the place. They have certain zones that they tend to hang out in, right? So we accommodate that. We get the day of the week, okay, and mapping different times into our different days of the weeks together. So we get down here and we can go ahead and merge all this stuff together. So we have our timestamps, our zones, day of the week, the hour, the bucket in the hour, XY coordinates. So we're all set there, the sine, daily, cosine, and the counts. Okay, so we need the count of requests here so we can see, try to understand like how close is an Uber driver to a rideshare requester, right? And again, we want to assign the car that is pretty much the closest, but it's not necessarily the closest if there's going to be a couple more people sharing this car and the car is going to take a slightly different path. Then you try to accommodate all these requests and optimize the whole problem simultaneously. Okay, so hopefully that makes sense. So moving on here, we're going to use a RandomForestRegressor to go ahead and make our predictions into the future, which cars can be the closest, and then pick that most of the time. But again, like we have to accommodate other requests if it's a ride share and there's a couple more people that are going pretty much the same destination as another person, we won't necessarily pick the closest car. We're going to pick the driver and multiple passengers that need to get to the same relative destination, kind of same spot, and optimize that kind of problem, right? So it is a little bit complex. It's nothing that we can't handle here. We can slice through it pretty easily, but it's not just simple, okay, this car is the closest and it's going to go to this rider, or this rider is close to the car, so we're going to assign those two together. It's a little bit more complex than that. Okay, so anyways, we have the RandomForestRegressor. So this is going to be our machine learning model. We have the train and the test sets. So I've explained this in a lot of my data science videos. I'm not going to get into it here, but basically you have training, testing, you do the split, and the X is going to be the independent variable and the Y is going to be the dependent, okay? So we go ahead and assign the cosines and the sines to the data frame, right? The bucket hours, the day of the week, the hour. Again, we're trying to understand what is the demand on the system here, right? And try to optimize the assigning of riders to cars to reduce driver idle time, right? So they can be busy most of the day and reduce the time that the rider has to wait for the car to arrive. Okay, so it's going to be a win-win situation when we get this figured out. So we're going to create down here a dispatch simulator. So we already have the grid from above. We know what this average speed is going to be in terms of where the Uber drivers are operating. If it's in New York City, it's probably going to be smaller. Slower than a smaller city with less traffic. So we have to accommodate that. So we have to know the distance between zones. I create a small function here to help us understand that. So again, we're using the XY coordinates, right? So X1, X2, Y1, Y2, this is the latitude and the longitude coordinates. So we know where all these cars are at any given point in time. We know the travel minutes down here with this function and the random neighbor zone. Again, if something just randomly happens in terms of another rider requesting a ride and this car is pretty close and already has one person in the car, we can go ahead and pick up this other person if they're going to essentially the same destination or somewhat similar destination. Okay, so we're going to run the dispatching, creating drivers pending, assignment logs, rider wait times, driver idle time. So these are all lists right here. We create a list and we're going to go ahead and append the results that we calculate to this list. So I tend to work with a lot of lists in data science and all the machine learning stuff that I do and analytical work that I do. So lists are great, data frames are great. Sometimes I use dictionaries as well. I don't use tuples very much, but that is another data type or data structure in Python that you'll see from time to time. I don't even see it used that much. But there is a time and place for a tuple too. This is a immutable object, right? I think the lists are just a lot more flexible, so I tend to use those. Tuples are okay, and sometimes they're useful, but most of the time for the work that I do, I don't even use it and I don't even need it. Okay, so we're trying to assign pairs between riders and cars down here. So the I and the J is going to show us all the rows and all the columns, combinations, and we're going to have a big matrix when this is all done. Okay, so you can see the matrix being built right down here. And again, when we have every combination of column and row and rider and driver, we can see the proximity of the rider and the driver, who's close, who's not close, and start to make our assignments based on that. And again, incorporate any other people that are kind of hitchhiking along, picking up in a similar origin and going to a pretty similar destination. Okay, so now we're starting to do our pending down here. This is the assignment log, so I'm appending to this. This originally comes from over here. This is a list I was just talking about just a moment ago. So we create a time assigned, the required time, the zone, the driver, ETA to pick up, driver wait time, driver idle time, and then the finish time. So we're taking all of these different data points and assigning this to the list. Okay, and down here we can see the mean average error when we run this model and how well of a job is it doing in assigning riders to vehicles. Okay, so the MAE is only 1.55. This is pretty low error. There's always going to be some error. The model can't always pick with 100% guaranteed accuracy which rider needs to be assigned to which car, but you can see with an MAE, mean average error of 1.5, it's pretty low. So the model has been trained and tested, and it's making predictions at this point, and the predictions are pretty accurate in terms of the holdout data set, right? You have the training and the testing set. The training set is the majority set. The testing is the testing for the computer, and then you compare the tested results with the actual results. That's how we get this MAE of 1.5 down here. Okay, so we can see that the training was done. The testing is making pretty accurate predictions, giving us a low error down here. Okay, so everything seems to be shaping up pretty well. I'm going to go ahead and create my charts and graphs at this point. Let me run this. Make sure everything went. Yep. Okay. So I think we are in good shape. I tested this before, but sometimes weird things happen, and maybe fat finger key. If you miss one comma over here, it's going to throw off the whole thing, right? So you have to be cognizant of what's going on here and careful when you're coding up these solutions too. When this is done and saved down and everything is tested and validated, we can put this in production and it's going to run fine. But during the testing phase, which is what we're doing now, or the development, the dev phase, like you have to be careful with these things, right? A small mistake can blow it up. So we want to go ahead and look at some bins of riders. We're going to have the number of bins as 30, and we want to try to understand the rider weight optimization time, right? So I'm going to create a histogram and throw all this data into the histogram and create 30 bins to see on average what these wait times look like. Okay, so I see minutes, 0 minutes, so less than a minute. So the car and the driver are pretty close. We see 86 here. Between 1 and 2 minutes, 111. Between 3 and 4 minutes of wait time, there's 73 people waiting, and more than 5 minutes, 17 people waiting, right? So this is the optimized dispatch. I'll show you in a minute what non-optimized would look like. Let me take you through a couple more steps of the code. Okay, so we have the histogram, we have the optimal and random. So this is how we can do the comparison and see how well the model is performing. If we optimize the model and don't compare it to some kind of baseline or some type of non-optimized solution, you're never going to know how well the model is performing, right? You have to go ahead and create the optimization, compare it to a non-optimized output, and then you can start to appreciate, okay, the model is working fine. The optimization process is saving me a lot of money, or maybe it's not, right? But without making this kind of comparison between these two, we just don't know how well the optimization is working, or is it even working to begin with, right? So what else? So we also have time assigned down here and the assign option. So we're going to put everything into hourly and then look at the total wait time real, total wait time base, save time total, and waited time total. Again, so we're going to look at all these different comparisons and these different metrics to see how well the whole optimization model here is performing. Okay, so we're going to look at mean ETA to pick up the rider, wait time, composition, what is that made up of, and the cumulative dollar savings. Okay, and then we can pass everything into a plotly chart, add some traces down here. So the traces kind of make the chart pop a little bit and kind of jump off the screen. And it just makes it more engaging and more lively, I think, for the stakeholder that's interested in this, or the end user, or whatever audience you are presenting this to. Okay, so I think we're almost done. We have the traces down here, cumulative savings versus hours. So hours is going to be on the x-axis, and savings is on the y-axis, right? That's pretty normal for time series. So here we have the counts again in minutes. Okay, I'm sorry. So first is rider wait time. Then we have the driver idle time. Okay, so 0 to 9 minutes, 238. So that's pretty decent, right? Like most people are not waiting. Some unfortunate drivers are waiting between 10 and 19 minutes. They're not getting any riders. 7 drivers have to wait between 20 and 29 minutes. So it's almost a half an hour. Then we get over half hour. This is 40, 50 to 60 minutes. So at this point, the driver probably gave up and took a lunch break. But we have 4, and actually, now we have 1 that waited over 100 minutes and 1 that waited over 160 minutes. So 120 is 2 hours, 3, 4, 5, 6. So that's like 2 hours and 40 minutes. That's a long wait time. The guy probably signed off for the day and just went home at that point, right? If there's no more riders, there's no more riders. What can you do? So the mean ETA to pick up the optimal mean time is 1.8 minutes. So this is what I was talking about before. This is why we compare the optimal solution with the baseline solution. The random non-optimized or baseline solution takes 2.38 minutes for the rider to get picked up. The optimized solution takes 1.88 minutes. Here we have a small warning. We can just ignore that. That's really nothing. It's just telling us that This H is going to be depreciated. I think that's hour. I'd have to look into seeing what that is. So something's going to be depreciated. That the code still works fine, right? It's just a warning. So we have to be mindful of this and probably update the code before this goes away for good. And then we're going to have an actual error. This is just a warning that there's an upcoming error when the switch is made. So this is it, guys. This is the optimal versus baseline mean ETA to pick up a rider. 1.9 minutes for the optimal solution, 2.4 minutes for the baseline solution, right? So non-optimized, so you save about 0.5 minutes, right? So half of a minute saved by using this optimization model. So I would say this is definitely working. The random forest regressor is definitely doing a good job picking the right assignments between riders and drivers, right? The total save time is 21.2%. Wasted time is 78.8%. And the cumulative dollar in savings is pretty much just monotonic. Monotonic means going in one direction without changing. So it could be up or it could be down. This is definitely up, monotonic. And as more time goes on, more savings are created, right? Because the model is making better and better decisions over time. It's saving more money by matching riders and drivers more quickly, right? And again, quite literally here, time is money. You don't want to be these guys over here waiting 40, 60 minutes, whatever. You want to be in this first bucket over here where it's 0 to 9 minutes, okay? And then I don't think there's going to be too many cases where it's 0 minutes unless you just happen to have a drop off and a pickup right on the same street corner. And if you can pull that off over and over again, good for you. That's great. But most of the time, there is going to be at least a few minutes downtime between drop-offs and pickups, right? And there's not too much you can do about it. But again, we have already optimized this problem, so we've reduced the wait time for riders to be picked up and the drive time or idle time for the drivers waiting around for a new call to come in. So that is it, guys. I'm going to wrap it up here. I will save this Jupyter notebook and post that on YouTube so you have everything you need. Hopefully this was informative and useful for you to understand how Uber is probably doing this. Again, I don't know exactly how they do it. This is one solution. It definitely works. Theirs might be, no, honestly, theirs is probably more complicated than this and probably more, a little bit more streamlined. I mean, I just took a first pass and I came up with something that definitely works. Now, you might want to try a few different models. I'm doing the random forest model over here. You can see that. Where is it? Random. Get rid of that. Okay. Yeah, RandomForestRegressor. So we could test different models. This video is not about testing multiple different models and see which one is performing the best. So in a real world scenario, you would want to test different models, right? And see what the output is. So the MAE over here, like I explained before, is pretty low. That's pretty good. So this model might be the best, but there's several different regression models that we could try. The XGBoost regressor works pretty well. Random forest regressor works pretty well. There's several that we could test and try and see what the performance is for each one and then pick the best one and implement that. This video is not about that. It's just picking one and seeing what the output is. So I'm pretty happy with this MAE and pretty happy with the savings down here in this chart. Only 1.9 minutes mean pickup time versus 2.4 if you don't optimize. So that's it, guys. I just saved this workbook as an HTML file. I will share that with you and you'll have all the code. You can do your own analysis and I'll put that a link to that notebook or the whatever, the HTML file, you know what that is, when I post a video a little bit later today. Okay, so thanks so much for your time. Thanks for sticking through to the end. I appreciate that. Let me know in the comments section if these videos are good or not so good. I mean, if you had a great experience, definitely let me know. If it's not a good experience, then don't tell your friends and don't post negative comments, please. There's too many negative comments on social media now, Facebook and Twitter, or I guess it's called X now. I don't even use that thing. Lots of negative comments on YouTube too. We don't need more of that. We need more positivity in this world, more optimism, right? So that's it, guys. I'm going to wrap it up. Thanks again, and I'll talk to you soon as I post the next video. Goodbye for now.